Assalamualaikum warahmatullahi ta'ala wabarakatuh. Hi everybody. So today we are going to proceed with lecture 9, our lecture 9. And we gonna talk about air movers and fan technology. We have discussed about this before in our previous lecture. But today we're gonna continue with the topic. And we're going to see the system characteristic. What is the relationship between system characteristic and system operating condition? We're going to see also the fan characteristic and what do system characteristic and fan characteristic do with operating conditions. So, all right. It is said that here, fan performance, in order to consider fan performance characteristic of volume, the capacity of airflow versus pressure developed, duct system characteristic can be examined as well. So duct characteristic of CFM, or actually it is notated as Q versus pressure loss HF. And the pressure loss due to frictional resistance in a given duct system does vary as CFM changes. And the formula that is used for the calculation to calculate the pressure loss due to frictional resistance, if you have two conditions, you have pressure loss initial, final pressure loss. Then you also have the airflow quantity, CFM, at the initial condition, and also CFM2 at the final condition. We can use this formula to calculate the pressure loss due to frictional resistance at the final condition. HF2 is equal to HF1 times CFM2 over CFM1 squared. Alright, so this formula is used to determine the pressure loss in a duct system if CFM is changed. Okay, let's take a look at this example. If we have a system that has a pressure loss of 2 inch of water gauge with 5,000 CFM of the air flowing, and what would be the pressure loss if the airflow were 7,000 CFM? So this question asks us to plot the system's air quantity CFM in CFM versus the pressure loss HF, starting from 0, 2,500, 4,000, 5,000, 7,000, and as a solution, you have to calculate for every CFM by using the formula that we discussed just now, which is HF2 is equal to HF1 times CFM2 over CFM1 squared. All right. So if the CFM is 7,000 CFM, to calculate the pressure loss at the where the air flowing at 7,000 CFM, then you just have to put every data in the formula. Therefore, HF2 is equals to 7,000 over 5,000 squared times 2-inch water gauge. That means at 7,000 CFM, you have a pressure loss about 3.9-inch water gauge. All right. Okay. So next slide. Okay, so this is the result where you have calculated for every point. We have 6 points here. 0 for 2,500 CFM, 4,000 CFM, 5,000 CFM, and 7,000 CFM. And as you calculate it, and you will get this result. And you can plot the graph. All right, now it comes to operating condition. How to get the operating condition for an air distribution system? Actually, when we plot the fan characteristic curve and also the duct system characteristic pressure versus flow curves together, by plotting the fan performance curve and also the duct system characteristic curve together, then where the curve intersects, that is the operating condition. You can read what is the airflow and what is the pressure for the at that particular operating condition. For example, here, I don't know if you can see my cursor, but if you can see the bottom one is the system performance curve, and above here is the static pressure fan performance curve. And as you plot the graph, it will intersect. Both curves will intersect at a point, or maybe more, but for this graph, it intersects at one point, and this particular point where it intersects is actually the operating condition for the system. Okay. In using curves, it is necessary that the point of operation selected represent a desirable point on the fan curve, so that maximum efficiency and resistance to the stall and pulsation can be attained. Of course, if we want to choose the operating condition, the optimum operating condition, we would want to have low resistance but high volumetric airflow rate. That's where the desired region where we can choose our operating conditions. Okay, in system, there are cases whereby there are more than one point of operating condition encountered during operation, and we have to look at the range of the performance and evaluate how the selected fan reacts within this complete range. Okay, if you see this curve that we have here in this figure 14, the gray area is actually the recommended selection region Why? If you see the dotted line in the first what we call the first one, the above one, then we can see that the dotted line will cross at quite high pressure loss. Okay, come back again. The above one, the curve with the dotted line, is the less desirable curve. Why? Because at this curve shows that the total pressure increase at this where it crossed the fan performance curve, but the volume airflow rate is low. But as the curves, the fan curves proceeds, we can see that the total pressure decreases. That means the resistance decreases and the volumetric airflow rate increases. That is why the desirable performance curve of system performance curve is actually the middle one. But still, there are certain range that we can choose, since there are several system curves that intersects with the fan performance curve. That means within this range, within this gray area, the operating condition is still acceptable. All right. Okay, this is an example of in figure 3. This is an example of the static pressure versus CFM of a system. There are two curves in here, which is a system performance curve, and the other one is a fan performance curve. And as I mentioned before, where it intersects, where those two intersect, that particular point is the point of operation, point of operation condition. And in figure 4, there are 3 fan curves and 1 system performance curve. And of course, it intersects at 3 points. So all these 3 points is the points of operation of the particular fans. It is to be noted that again, you have to see the static pressure has to be low and the CFM has to be high. That is the most desirable condition. If you have several points and you have to see which one has the lowest static pressure but higher CFM. That is the point that is suitable to be selected as the point of operation condition. And there are a number of relationships among fan performance characteristics for a given operating at change condition. Sometimes the operating condition changes. So we have to see, we can predict actually what is the fan performance by using certain formulas at that change condition. And we call this as fan law. And there are also times where we use different size fans for similar construction. So we will see in the next slide what is fan law. So this relationship are called fan laws, and these relationships are useful for predicting performance if the conditions are changed. Okay, actually I have two examples here, but we will be discussing only one, and the other one I want you to try to solve the problem by using the fan laws that I'm going to explain in a bit. All right, so the question is, a fan was originally installed to deliver 10,300 CFM at 2 and quarter inch of static pressure, inch water gauge of static pressure, and to run at 877 RPM, that requires 5.2 brake horsepower. But after the installation, this one is the design condition. But after installation, it is found that the system only delivers 9,150 CFM at 2.5 static pressure, 2.5 inch water gauge static pressure, and it only uses 4.7 brake horsepower. This indicates that the original calculation were in error, and the system was not, or maybe also the system was not installed according to plan. The question is, what fan RPM and BHP will be necessary to develop the desired 10,300 CFM, and what static pressure should have been configured? All right, so let's really understand the conditions. Now, you have to bear in mind that in plan, we are planning to have 10,300 CFM at 2.25 static pressure at that revolution per minute and at that brake horsepower. But this condition is not achieved. After installation, the CFM is lower, the static pressure is higher, but the brake horsepower is also lower. If we look at the fan law, we have several relationships. You have to determine that situation has constant size and variable speed, or is it the situation have a constant speed and variable size? What is size? Diameter size of the fan. Okay, actually the blade of the fan. So the diameter of the blade of the fan. So in our situation just now, we can say that we have the same, just a minute, we have the same fan. Now we have the same fan and we want to use the same fan in the installation. We do not want to change the blade size. So now we have a constant blade diameter size of the blade size of fan, but what we would want to change is the speed. So as we look at the question, we know that Now we have lower CFM, the lower desired air quantity. So now we want to increase the air quantity. The most suitable solution is to increase the speed of the fan. So the question asks, what is the fan RPM, the new fan RPM, and also the brake horsepower that will be required so that we can achieve this 10,300 RPM. And later on, we can calculate also the static pressure of the fan, of the new operating condition fan. Okay. First, what I would do is, we have this relationship Q1 over Q2, where this is the airflow quantity, volumetric airflow, is equals to N1 over N2, where this is the revolution or the speed of the fan. All right. So now we have this relationship Q1 over Q2 is equals to N1 over N2. So you know that the desired, where we can notate as Q2 is 10,300, and the Q1 is 9,150 CFM. We want to see what is the RPM or the N2 actually to achieve the 10,300. So the formula is, when we put all together, then we have 10,300 CFM over 9,150 CFM is equals to 877 RPM over N2. And then we would get N2 is equals to 10,300 times 877 over 9,150. Let me calculate for a bit. If you have calculated, then you can also calculate. We have 987 RPM. 987 RPM. Okay. And the question also asks us to find what is the brake horsepower. And you can use the third equation, which is HP1 over HP2 is equals to N1 over N2 with the power of 3. And this HP is actually the horsepower. In this case, we use the brake horsepower. Horsepower is the output of the fan. The brake horsepower is the input, is the energy consumption that we use for the fan to be operated. Sorry. Okay, so we use this equation, this relationship. So HP1 is 4.7. All right. So we have 4. Okay. So as we can see here, the brake horsepower is 4.7. BHP1 is 4.7. And the desired BHP is yet to be found. So BHP2 is what we want to find. And the N1 is 877. And N2, what we calculated before, is 987. That means we have 877 over 987 with the power of 3 is equals to 4.7 over BHP 2. So we can find the BHP 2 now. You can calculate 4.7 over 877 over 987 with the power of 3. Okay, you can calculate later, I think. All right, as we calculate, we have the BHP 2 is equals to 6.7 BHP, brake horsepower. And the last item that is needed to be calculated in the example is the static pressure. And we have the second equation here where P1 over P2 is equals to, or the pressure 1 over pressure 2 is equals to the revolution per minute N1 over N2 squared. And we can calculate the P1. It is given that the P1 is equals to 2.5 static pressure, right? So we would have 2.5 over the static pressure 2 is equals to 877 over 987 squared. All right, so let's calculate for a bit. 2.5 over 877 over N2 is 987 squared. Okay, is equals to 3.2. So we have here 3.2 inch water gauge of static pressure. All right, so the next example you can try to calculate by yourself by using this formula. First, the first step is to see what is the constant. Is the blade size of the fan is constant or the speed is constant? And there must be only one constant. If the size of the blade of the fan is constant, then the speed is variable. And if the speed is constant, then the size of the fan blade is variable. According what is the constant, then you will use the equation in the boxes. If the speed is constant, then you'll be using the three equations below in the table. All right, I think that's all from me for this session. And inshallah, if you have question, you can ask it later in our face-to-face session via WebEx or maybe Zoom. Thank you.